And, you know, if you want to, if you're looking at an old test or something like that, I'll put that for you. Fall 2012, exam 3. Okay, so this is this about a surface area of the cone?
Yeah.
Okay, so this is number 5, fall 2012. It says the surface area of a cone, not including the base, is given by this formula. S is pi r times the square root of r squared. So h squared, where r is the radius of the cone and h is the height. Find the cone of maximal surface area, not including the base, that can be inscribed in the sphere of radius r. It's a mess. So here's a cone. So this is kind of a good one. And I am going to be very sympathetic to getting stuff set up. Right. So draw me a picture, walk me through it when you're doing the test. Remember, part of what you're learning in mathematics and in engineering is communication, right? Good, right? Because it doesn't matter if you've got all the knowledge in the world in your head, you can't tell other people that do anybody good, except maybe you. So if you have a cone, radius r, height h, I gave you a formula for this, it's just given. S is pi r. So it's a sphere, pi r times the square root. So this is, you can just take that as a given, that is given to you. Find the cone of maximal surface area that can be inscribed in the sphere of radius r. Okay. So now I'm going to put this thing inside a sphere of radius r. Get this cone. And notice there's many ways I can put it. Inside the sphere. This. Now there's many ways I can put this cone in here. I make it tall and skinny, right? Or I can make it short and fat. And the question is, how do we make this as big as possible? So what we're trying to do, find maximum. And let me do a little bit more drawing on this. The radius of the sphere is capital R. Radius of the cone inside here, little r, and what should right there? Height of the cone is h, and the radius of the sphere is r. So you got all this stuff going on. H and R can vary, right? But the radius of the sphere is always the same. It's the same sphere we're trying to step inside, right? Everybody kind of got a feel for that. Now, what we're trying to do, we're trying to maximize the surface area, which is pi, little r, square root, r squared. it doesn't change the picture, but if I had included the base, I would tack on an extra pi r squared there. Which would, actually, I'm sure the reason I did that is to make it less complicated than it's going to be anyway. Okay, so what do we need to do? Right, so somehow, what's our problem? Our problem here is we've got too many variables. We've got little r, we've got relate, right? There's got to be something that relates them. Any ideas? Yeah, that's how we can relate little r and relate. I agree with this picture. Maybe we need to read it. I mean, the picture's right, but it's not as helpful as it could. What's it? More pictures for any part. As is often useful, I'm just going to look at cross section. So this is cross section. What's this right here? Here. What is this distance from here to here? That's the radius. Right, dark red up there. So, and this distance from here all the way to the top is the height. So notice this right here. Can you figure out what this is? Right here? What's this? Isn't that a right triangle? So isn't this? Okay. So. Does that help us get the height? Well, okay, so let's call it circle x squared plus. Here's another one. I call this point x y. This is the point on the circle. What does the x coordinate represent? It's the same thing as R, isn't it? Little What about the whiteboard? Close, right? If you look, if you consider this coordinates on a circle, this is 0.0 r, right? X coordinate 0, y coordinate, right? So if you measure this minus the y coordinate here, or minus y equals height. Right here. I think I want to kind of revamp this in terms of X and Y. So let's look at our S. You could go through and do one before. Let's look at this S. S in terms of X and Y coordinates is because the radius is the X coordinate. Comes square root of R squared, so that's an X squared again, plus H squared, which is everybody agree with that? I replace X with R and I replace H. Okay, so now I know how everything relates to each other. I've still got my too many variables problem. Let's see what this looks like. This is X squared plus R squared minus 2RY. Now this simplifies it. Does anybody see a trick we can do? What is X squared plus Y squared? So this is a little bit simple. There's an R squared and another R squared. And now, let me ask you a big question. Here's a big question. I've still got too many variables, I gotta get rid of one. You want me to solve for X and replace the X, or solve for Y and replace the Y? And can you justify why? Might be a good idea. I would replace X. And the reason is I don't want Y under a double nested square root. So my surface area is pi. I'm going to replace X by the square root of R squared minus Y squared. And then I've got this other bit, square root of 2R squared minus 2RY. Yeah, but you need to be we want to maximize this. By the way, before I simplify this, what's my flavor? Nobody's water. let's see, y can be, actually, I can go further than that. I can go y to be negative r. Y all the way down here, negative r, all the way up to positive r. This is also another good reason to pick y, because x is more ambiguous. It's like some of the other triangle problems. Triangle here with this x coordinate also has the x coordinate up here. But y is, when you tell me a y coordinate, I know which triangle. So maximum this on that interval. Now, the next step is going to involve taking a derivative. Why do you not want to do this? Squares will be off, right? And then watch us go through it. You think the way to make this easier. What's that? What's that? That's right. Because you want to make the surface area as small as possible, right? That's the same thing as making the square of the surface area smaller, right? So what you do is we can make the square of the surface area as small as possible. We go back to the square. That'll make your computations easier. But A will square of S. So now A I squared R squared minus Y squared times 2R squared minus 2RY. And range for Y is the same. This is much easier. Right? No square roots. I'm going to find the smallest one, and then I'm going to remember that my answer is the square of what it should be. Okay, so this is a product rule, so it's minus 2y, that's just garbage. Plus pi squared, r squared minus y squared, that's the derivative of this, which is minus 2. Everybody okay with that? Because remember, there's a lot of R's in there. Remember, those are just numbers. Okay, any questions? You were vexed. Minus 2y. Okay, pi squared is just a number. So this is product. Derivative of this. Yeah, R's are constants. Derivative of this is minus 2y other bit. And then this times derivative of this. Right. Remember that, because whenever you remember, your life turns easier. Okay, everybody okay so far? I'm gonna pull out a pi squared. It's obnoxious. This thing's made with I should pull out some more too, I guess. I'll pull out pi squared r minus 2y. 2r minus 2y. So pull the r out of this one. Plus this one minus 2 squared. Pi squared r, all right, let's see what this make. This is minus 4ry. This is plus 4y squared. Minus 2r squared. Plus 2y squared. Which is pi squared r. This is going to be so I've got 6y squared. And I've got minus 4y 16. So a mess, right? So this should be something. 3 lines, this, and -6. That's 6y squared. Minus 3ry, or minus 6ry plus 2ry is 4y, and minus. So now, almost they occur y is equal to minus r over 3, 1/3 of negative r, and I guess we're going to use r. And this one doesn't make any difference because I've already got, I was checking it in. We have 2 critical numbers. Let's see what I got there. Now, I'm digging on this because this is a continuous function on a closed interval. So all I got to do is I got to plug in the critical points, plug in the endpoints, and have the contest. See who's the biggest, smallest. Well, so let's do A minus R, A R, A minus R over 3. Well, when I plug in negative R here, I get 0. When I plug in R here, I get 0. So both of these are 0. And this doesn't surprise me because when I put this cone inside here, when Y was negative R, it was tall thin, which I don't think that much surface area. And when A is, or when R is all the way up top, when Y is R, then that's just point at North Pole. So this is here. If this gets a positive number, it's minus. Let's see what happens when I put this in. I get mass, I get pi squared. I'll put this in. This is going to be r squared minus r squared over 9. So this is going to be r squared minus 9r squared is 8/9 r squared. And for this other bit, I'm going to have 2r squared minus 2r times 3rd r, so that's plus 2/3 r squared. So it's 2r squared plus 2/3. Yep. So I get pi squared 8/9 r squared times, this is going to be 8/3, isn't it? So I get pi squared times 64/7 r4. And that actually reminds me, that I didn't hear maximize R or the surface area. I've actually maximized the square of the surface area. So the maximal surface area. Everybody okay with this? turns out to be whatever the square root of this is, like 8 pi over 3 radical 3 r squared. And that's the right unit for surface area. It's the square p. And let's see, I guess your height was 4/3 r. Because my height was r minus y, so it's plus this, and the little radius of this is my x coordinate, which is square root of r squared minus y. So it's 2 radical 2. This is right area. Square that, it's 8/9. Oh, yeah. So I'm not really sure what was asked the question because I was ambiguous on that. And by the way, if what I'm asking you a question is ambiguous, ask me because I don't want to try to fool you that way. Anyway, so there's your maximal surface area. It's this, and you create this by having a height of 4/3 r. Question. Well, you came right out of the gate on that. That was not. Let me throw out a couple. By the way, let's play dynasty one now. Let me throw out a couple for you. The first, Grace, you and I talked about this. So here's a maximum problem. Suppose I give you a T square of length L. And what I want you to do is you take a pair of scissors and you cut this wire here and you turn one of the pieces into a circle and one of the pieces, what's left over, into a square. So I don't know what you do, but you make the person separate something. You take a piece of wire, you cut it. What piece you turn into a circle? How to cut the wire to make the maximum total area and the minimum total area. Before we start this problem, does anybody got any intuition on either of the answers? So this is clearly a max min problem because there are these words. But the important thing is, I think, is getting this set up. Right? You need to draw a picture, maybe communicate your ideas. More importantly, you can understand yourself what's going on. Now, here's my wire. It's L units long. And my exercise is to cut it. Turn one piece into a circle, one piece into a square. So what does that suggest that we do with this picture? And I guess the question was, how do we cut it? How to cut it, right? I mean, there's a couple things I could do. I could not cut it at all and turn the whole thing into a circle. I can not cut it at all and turn the whole thing into square, or I can cut it right down the middle, circle and square, somewhere in between. What seems to be an important thing underneath the problem? Right, we need to know where to make the cut. That's going to be the variable, right? So let's suppose that X is, make the cut here. So this one is X. We'll use this for the circle. And we'll use this bit for the square. Now I could call this Y, right? I got to call it something so that I know what I'm doing in my problem. But there's a better thing that I can call it. If I'm going to call the piece that I cut off with the circle X, what can I call what's left over? There you go. Not exactly minus X, but how about L minus X? Because when you put those two pieces together, you should get L minus, right? This is actually, I would have had to come back later and solve my two variable problem. But I think I've circumvented this already. Because instead of calling this Y, I said, hey, this piece and this piece got to add up to L, so this is X, that's going to be L minus. Now, how to make the circle? I'm not going to worry about what it did, but I have this length here, X, and somehow I take this down here and I make it into a circle. Now I'm going to need, the area of that circle. Ooh, I know what area is. R squared. This is the area of the circle. Why is that not exactly what I want at this point? Certainly right. Well, there's nothing wrong with my formula, but why is my formula not completely useful at this point? I need this formula in terms of X. That's the variable I'm talking about. But what have I got R? How in the world am I going to get X out of this? The length all the way around this thing is X. Everybody agree with that? Because that's the length of the wire that I cut off. And this X, which is the trip around the circle, is the circumference of the circle. It's clear. Remind me what the circumference of the circle is. 2 pi r. So now this formula lets me turn R into X, which is what I need. So R is X over 2 pi. So my area of the circle is pi times X over 2 pi squared. Or if I like, X squared over 4 pi. Now, what about the square? I've got to take that piece I've got left over and fashion it into a square. And I need the area. Oh, look at me. I'm just burning it up with formulas. I happen to know the area of the square. But I've still got the same problem that I had before. Right? S, it's not in terms of what I want. I want to measure this in terms of cuts I made on this wire. There you go. The perimeter of the circle is 4 lengths of S. Everybody agree with that? But it's also the length of the wire, which is L minus X. So I get S is L minus X over 4. So my area of the square is equal to S squared. Well, square of s, which is L minus x. Funny squares. Do I get so far? Okay. What's the total area? Right? That's what we want to max and then the total area of this. I'm going to call this just plain A, total area. That should be the circle. And this is L minus X squared over 16. And I can tell you now, just looking at this, well, one minute. What's our playground? What value is X? Remember, X is where I cut this Y. So what values of X are appropriate? 0. And what does it mean when I think X is 0? It means I made the whole thing into a square. Do I agree? And L is as big. And what does that mean? All circle. And everything in between is a compromise. A little bit of square, a little bit of circle. Right? And I can tell you, just from looking at this will have a minimum inside the interval, part square, part circle. And the maximum will be either all square or all circle. Just like that. Let me take this one more step further. 1 over 4 pi times x squared plus 1/16 L squared minus 1/8 LX plus 1/16 x squared. Now I know that looks like alphabet soup. It's terrible. There's lots of letters there. The only variable is x. Explain, describe to me what this function will look like were I to graph it. And that would be perfect. Can you give me a general description? Again, it's a little more complicated, but let me prove this one more time. X squared. By reading this out. What we should call the graph of this. Right, it is. It's a parabola, isn't it? So is that. Do I agree? Happy. This one, very sad. Right? Because it's controlled by what multiplies the external, whether it's round here, happy, right? That's what this is. Let the letters throw you off. Number times x squared, number times x. And here's the big thing. Look, you said with the number multiplying x squared. Certainly positive, right? So this parabola is happy. So I'll promise you what's going to happen is, I don't know where it'll be something like this. We'll have them in, it's probably going to be in the interval, and one of the endpoints will get the max. Let's see this come to fruition. Certainly, I would take this argument if you were doing this problem. Let's see what happens. And this is actually a good argument. Y'all remember when we talked about curve sketching? I talked about the second derivative test. I kept kind of giving it, kind of just a little bit. This is one instance second derivative test is actually useful because I don't have to plug anything in. What you would want to do is, so let's get the critical numbers, which is unfortunate. I'm going to multiply this. This is a prime is 1 over 2 pi plus 1 over 8, 1/8 x, multiply 2 through there, minus 1/8 L. That gives me a critical number. Now let's see if it falls in the region that we want. Set this equals 0. What I get now is one over 2 pi plus 1 over 8 x equals 1/8 L. You know what I'm going to do? So x equals 1/8 L over 2 pi plus 1 over 8. I'm gonna, this fraction confuses me a little bit, so I'm gonna multiply top and bottom by 8 times. I'm gonna multiply the top and bottom by 8 times. So I can get some, look at it better. And this gives me pi L over 4 plus pi. So I get critical number. X is equal to pi over pi plus 4 times L. Am I agreeing with that? Now here's my question. Is the critical number in our range? Critical number might not even be in our playground. Is it? What do you think? Everybody, is everybody okay with this critical? Okay, let me ask you this. Is my critical number positive? Yeah. So I got this part licked, right? It's greater than or equal to 0, right? The maybe itchier part is it less than or equal to L, but it is. So I explain why. That's right. This is ballpark. This is about 3/7 L. Right. So it's like a little bit more than well, a little bit less probably than halfway across the end. Right. So this is in the interval 0 to L. And here's how I would figure it. Here's how I would do this problem. A of 0. That's the all square. Let's see what we get. When I plug in 0 for A, or I'm sorry, when I plug in 0 for X, I get 0 here, and I get L squared for 16. Or yeah, I get 1/16 L squared. When I plug in L, this piece drops out, which makes sense, and I get L squared over 4 pi. Which one of these two is bigger? I agree. It's got a smaller denominator. Do I agree with that? Everything else same, smaller denominator. This is the maximum. The reason I know that is because critical number is absolute min or prime. So notice the problem actually, when I say the problem, I didn't ask what the area was. I just wanted to ask how to cut it. Here's how you do it. You want that area to be big as possible. You make it all square. You want it as small as possible. Then you let X, here's the length L, go about 3/7. Well, actually, close to that. About 3/7. Make that part of the square and then part of the circle. Here's my plug for the second derivative too. Notice that A double prime is 1/2 pi 1/8, which is positive. So that means that that number actually should give a local minimum. It's a continuous function, and that's the only local extreme that has been absolute. Any questions? This is related to, where do y'all sit at the movies? Sit down front? Sit all the way in the back? Where do you sit? You sit all the way in the back. So what's your motivation? Where you sit? Easiest to what? Get snacks? Pizza, movie theater. That's good work. But let's suppose that you were, I don't know, weren't eating, right? You want to sit where you've got the best view, right? What happens if you're too close to the front? Yeah, your neck's in pain, you can't quite see anything. And you know, I mean, the back's kind of okay for a movie theater that's got a big screen, right? But if there's like a mile's worth of seats, right? I mean, how many of you have ever gone to the rock concert or something that set at the back, right? You can't even see what's going on. Yeah, I can remember my brother telling me, because my brother likes to go to, like, when he gets the opportunity to go to pro ball games. He started getting seats that were more down front. And he says the first time he did it, it amazed him because you don't really, you're sitting watching a basketball game, pro basketball game, back, you don't really realize how big this guy is until you get down on the court and you see that really are pretty tall people. So here is a problem that is motivated like this. I'm going to simplify it a little bit. You are at an art gallery. Admiring a painting. Your favorite Jackson Pollock painting. And so suppose you're the only one in the room, so you got nobody in your way. Where do you stand in front of the painting? Where do you stand? How far from the painting? Get on with you. And we will assume that the painting is H feet tall and A feet above your eye. So maybe you've got a painting that's mounted on the wall, and the bottom is here, and it's a really tall painting. I mean, if you stand here to look at it, you're going to be very disappointed, right? And see. And if you walk 2 miles and try to get your binoculars to look at it, you're going to be disappointed as well. So doesn't it kind of make sense that if it stinks to look at the painting when you're this close, and it stinks to look at it from 10 miles away, if you back up, at some point, voila, you're going to have your best view, right? It kind of makes sense, doesn't it? But the first thing we're going to have to do, I think, is agree on what this even means. What do you mean? We're supposed to need to have an optical view. I think that's right. I think that's the best way to do it. So let's kind of label something up. Okay, so here I am, before I discovered pizza, and here's my eye level. And we've got this painting on the wall. That's supposed to be straight. Let's kind of get the gist of this and make it. And this is 8 feet above my eye level. Now, what is my optimal view of this painting? I think we hit it right on the head. Because I want to maximize this angle. Right? That when that angle is as big as possible, it fills my vision. So that's what I'm doing. Notice if you think about what happens, imagine me walking up there. If my face is right up against the wall, my angle is very, very small. Right? And if I'm 10 miles away, my angle is very, very small. Somewhere in here, the angle is probably as big as possible. By the way, this is probably. So, question is, what else perhaps should I label, given kind of what I've set up? I mean, the question kind of gives you a hint too. Where do you stand? That is, how far from the thing are you when you've got the optimal view? So I think it might be prudent of me to list labeling how far away I am from this painting. Okay. Well, how about that? Let's call this X. That would be my distance from here. X can change as the problem goes on, right? Because I can walk toward the painting, walk away from it. But this do not change. A and the H. What's in it? Right? I can certainly do that. But, you know, here's my question. Given my X, which I think is going to be my variable, and maybe A and H come in there somehow as well, how in the blue blazes going to get an equation for theta in terms of X? Ah, that's right. That's right. But see, here's the problem. It's not a right triangle, is it? But you're absolutely right. See, here's the thing. That's a great idea. Let me call this angle. Now, the triangle here is not a right triangle, right? That's what's, I wish it was, but it's not. But this whole big triangle is. And so is the one on the bottom. Everybody agree with that? So let me write down something very silly and naive. I feel like a little tool writing this, but I'm going to do it anyway. Theta is equal to This angle is the whole angle, take away the little alpha angle. Now, what's useful about that? Well, now, big angle and alpha both come out of right triangles. So now I can steal your idea about the tangent. Because, look at that triangle. Tangent of alpha, tangent of theta plus alpha. You can tell me what tangent of alpha is? Great. It is A over X. And how about tangent of big angle? Well, you gotta have a whole. There you go. You gotta have a whole. It's H plus A over X. So this gives me forward. Alpha is the inverse tangent of A over X, and theta plus alpha is the inverse tangent of A plus H. So this is all just trigonometry so far.
How did you get that?
This one right here. Oh, this right here. Well, so theta plus alpha is this big angle. Right? So what that equation says is this angle on top is the whole thing, the big angle, take away the blue. That's all that equation says. And I'm going to go back to this equation because now what I have is theta this thing is inverse tangent A plus H over X. And then we've got to subtract off alpha, which is the inverse tangent of A over X. There we go. Everybody okay? This is what we were trying to maximize. What should I do now? I need to think about my playground. How small can X be? Isn't it? Right, except for, I mean, it sort of can sort of repair the zero, but you got a problem. I mean, I guess technically, if I smack my face against the wall, we kind of can't see that. Right? How big can this? Eat your carrots, it can be as big as you want, right? You can walk as far away, there's nothing stopping you. I mean, we ignore the curvature of the earth. And if you look at the picture that we created, it should be obvious, I hope, that there's a maximum in there somewhere. Because as you go way off to the end of this interval, bigger and bigger and bigger, that ain't small. And if you get really, really close to the board, right, when you get really in here, that angle is very, very small. It's just a sliver, right? So you should be getting max. In fact, I think we're only improving. Okay. This is devastating, but let's bite the bullet. The worst part about this is the secret X is the denominator. Actually, that's what I thought later. Okay, somebody remind me, what is the derivative of the inverse tangent of blah? 1 over 1 plus whatever the blah is squared. Good. But I'm not done. I gotta multiply by the derivative of what I find inside there. And this is just number over x. So this is number times x minus 1. So the derivative of this is minus a plus h for x squared. That's the minus 2. And the derivative of this, 1 over 1 plus blah squared. Now derivative was inside, which is negative a over x, like that. Now, this looks awful with these x's in the bottom of this here, but actually this x multiplies through this bottom and really kind of saves our place in the following sense. This is negative a plus h. X squared sweeps through here, telling this x squared, and x squared plus a plus h squared. The two minuses cancel here, and I get a over x squared plus h. Any questions? Now, I've got two fractions, denominators here. Here's a cool thing. Denominator can never zero. X squared plus positive constant squared. So, find critical numbers. Set the C to 0. See what happens. When I set this equal to 0, I get, bringing this over to the other side, by the way, so if we're looking for critical numbers, what do we do with solution to this? It's awful. It's not so bad. What I'm going to do is remember how the two fractions to be equal and then cross multiply. That's what I'm going to do. These two cross multiply here is a x squared plus a plus h squared. And that should be this cross just a plus h x squared plus a plus h a squared. And this requires this plus step out. This is a x squared. This is a squared times a. This is 2a squared h plus h squared a. And this is a x squared plus h x squared plus a plus a squared h. And it is a pretty good one, right? And that's provides 11. So here's what I get. Hx squared over here. So I've got you checked off. I'm going to take you over here. subtracting a squared h plus 8h squared. Now divide by the h, and I get x squared, a squared plus a h. So I get x is simple out of that. Notice there are two square roots, a plus and a minus, but the minus doesn't concern us because my x is two. I don't want to walk through the wall, right? So the negative square root. Now, what do we get? We got one critical number. There aren't any inputs to check. But what's the important thing that I need to do? Remember, our problem is maximize, right? What if this answer gives me a minimum, right? Wouldn't that be embarrassing? Now, there's several ways you can make this argument. I'm gonna do one that's this problem. I will take. You can argue that there's only one critical number here. You discover that, so there's supposed to be a maximum because it's getting smaller this way and it's getting smaller when it's very close to the board. Or you can look at the reason I might want to skip into the first derivative is because it's fairly complicated. But let's look at the first derivative. This is the way that's really the most mathematically correct. Theta prime is this thing, which is, well, let me run that. X squared plus a plus x squared. H plus a over x squared plus h. Well, this is equal to x squared plus a plus h squared times x squared plus h. I've got a common number. I got minus a plus h x squared plus a squared. Yeah, and I've got plus a x squared plus a plus h. Right. What's that? Here's the first derivative, right? Now we're over a common denominator. And so what I actually did here is, well, I don't have any linear terms. I just have x squared. So I get minus, actually, I'm going to stop writing this because this thing on the bottom is positive. So I'm just going to write that positive. Right. This is going to be minus a x squared minus a cubed minus h x squared minus h a squared plus a x squared plus a cubed plus 2a squared h plus a h squared. Very similar to what we had before. Got a positive denominator. Those kill each other. They get minus h x squared. That's the only x squared thing I've got for that. The a cubes kill each other. And plus 2 a what's it in the well it drags it down. This is a squared h plus H. Now, this critical number happens somewhere here. Square root of A plus H. It's somewhere between 0 and 10. Let's look at the first derivative. What happens when you're stinking close to 0? Well, positive here, and that's almost 0. So when you're close to 0, positive, so you're 0 all the way up. What happens when when X is huge? Well, these are positive, but since H is positive, if X is going to infinity, this is basically going to be negative all the time. And so way down here, it's negative, so it's got to be negative. So this gives a local max. And so it actually is an absolute max. But I will take other arguments for this as well. But this is kind of an equal formula. You've probably never seen this before, but if you have a baby that is 8 feet above your eye level and the painting itself is H tall, you take the 8 and the A plus H multiply, take the square root of that. That's how far away you should stand. It's the maximum. Okay, any questions? Yes. Okay, so what did you get? Oh, well. So, AX squared squared squared. Oh, I see. This is A squared H. H squared. That's an A squared H. And so cancel that with this. But actually what will happen is it's A squared H cancel one of these. And then because there's 2 of them.
I was curious, Brad.
Yeah, it's easy to make that square, sure. Okay, what else y'all got for me? Oh, is it the we know the tangent? What is this? So here's the question. We know that the tangent of a 45-degree angle is 1. Use differentials or linear approximation to estimate the tangent of a 42-degree angle. Is your estimate too large or small? What's the first thing that you thought you'd do with the problem? So, so here's I'll kind of capture the essence up here. Tangent of 45 degrees is equal to 1. Estimate using differentials or linear approximations. Tangent 42 degrees is estimate too large or too small. What's the first thing? So I was being professor doing this. What's one thing that I'm finding in part? Well, right, but there's something about these angles that's bad. We need to put this in terms of radians. Right? What's the derivative of sine x? Cosine x, right? That's in radians. Do it in degrees, it's something like cosine x times pi over 180. So 45 degrees. Anybody know how many radians in that? Power 4. What about 42? Yeah. 42 is to 180 as x is to I, right? Right. 42 is at a half circle, is an x is a half circle. Right. So yeah, that's right. I remember that. You multiply by pi over 180. This is 42 pi over 180. And I guess we can make that really simple. 7 pi 30. Actually, you know what I'm going to do? I'm going to call this 42 pi over 180. I'm going to call this 45 pi 180. Simplify my fractions later. Okay, so I'll use differentials. Again, you use the tangent line or whatever. So let me write down the naive thing. Tangent 42 degrees, 45 pi over 180 is equal to tangent of 45 pi over 180 plus delta y. I basically just said a bunch of nonsense. All this says is what I'm looking for. The tangent of 42 degrees is equal to the tangent of 45 degrees plus a little change in y. And it's our job to find out what that little change in y is. Notice my function y is tangent x. Right, that's my function du jour. Agree? Now, and by the way, somebody reminded me, this is kind of an angle. What the tangent of 45 degrees, power 480. I was going to ask you that. Now I remember it's problem. So here with differentials, what do we do? This is kind of a nonsense statement that what we want is what we know plus a little change. And my little change, here's the calculus part, the interesting part. I'm going to use differentials to estimate this. So if y is tangent x, what's the differential dy? Okay. Secant squared x times dx. And don't forget that because that's a little change, right? To make this work, my anchor x is 45 pi over 180. What is my dx? So my anchor, the anchor place where I know the answer is 45 pi over 180, right? How much do I have to change that to get where I want? Oh, you didn't miss the negative. Good. That's right. You got to back that up. 3 pi over 180. Remember? This is back. Take this, add that to it, I get back to 42. So let's just kind of shove this in and see what happens. Let me think here. The secant, well, let's see, the cosine of power 4 is 1 over radical 2. Secant radical 2 squared is 2. That's the secant of 45. And the x is minus 3 pi over 180. So I get minus pi over 30. So it's like a little bit more than about 10, I guess. Yeah, that's- So my tangent, so I would estimate so it's a smidge less than 0.9.
What method? This don't remind me of linear function.
That's exactly. Yeah, it's exactly the same. This is equivalent to finding the tangent line. The difference in actually the implementation is I plugged in the dx here instead of plugging in the x coordinate 42 pi, or 42 pi over 180. But you can do the tangent line. I'll do it alternatively that way. I like doing differentials just for the following reason. I'm more comfortable with them because they're the ones that are easier to use if you're ever trying to measure relative errors.
So this is differentiation.
This is using differentials. Linearization is the same thing, but for linearization, it's the same approach and really the same outcome. Lx is f of a plus f prime a times x minus. And remember, all this is just the formula for the tangent. So in our case, f of x is tangent x. So f prime of x, secant squared x. And here a is 45 pi over 180. It's the anchor point where I know this. So the linearization, assuming that f of x is approximately linearization, which in this case is tangent of 45 degrees of 1 plus f prime of 45, we already figured that out, that's 2 times x minus 45 pi over 180, which is my angle. And look what happens. F of 42 pi over 180 is approximately equal to L of 42 pi over 180. 1 plus 2, x is 42 pi over 180 minus 45 pi minus 55 over 180. And that part is familiar because there's that piece there subtracting 1. So of course you get the same answer.
I just like that method. Maybe square six to me. I don't know. Because the function I could just follow it easier. You know what I mean?
Sure, whatever function. But like I said, excuse me, if you get problems with relative error, I just find the differentials easier to manipulate. Estimate, too big or too small? Let me remind you what tangent is like. I'll try to draw a good picture. I'll show you verify that. Power 4 is not right there. Use the tangent line. Estimate. Tangent 42 degree, which is a little less. The rest too big, too small. Because the blue tangent line is actually under the curve. So f of x is tangent x. F prime of x is secant squared of x. And f double prime of x is 2 secant x times derivative secant, which is secant tangent. And this is positive between 0 and power 2. So it's concave up. So since it's concave up, that means that curve lies below the tangent line. It's, okay. Everybody, is that clear up for you, Chris? Okay, what else we got? Follow 2006. This is the one about the cylindrical barrel full of goop, right? So here is cylinder. So I'll read the question first. A cylindrical barrel is full of fluid of density rho. If the barrel is tipped so the base is in a plane that is an angle of theta with the ground, and the force on the bottom of the barrel is given by big formula. Where R is the radius of the circular base, H is the height of the barrel. What is the maximum force on the bottom of the barrel? And at what angle is the bottom most likely to fail? Anybody ever like, dumped an old factory and dumped over industrial waste?
Yeah.
Thank goodness, I'm glad it's done this. If you've ever pushed over like a barrel full of something, right? Actually, have you ever like tipped over a cup, like one of those cheap cups you get at McDonald's or something, had the bottom fell on you and sit for a while? Right. Usually it doesn't fail when it's sitting flat, but if you tip it over, it fails, right? So it turns out that if you have some barrel type H, radius R, and you fill it up with goop in here. It's got some density. I mean, it could be water, mercury, whatever favorite toxic thing is. It turns out, and so you've got this thing full, and then you tip it. So but now you've got a tip at an angle around the next theta. Right. When theta is 0, it's sitting the way it's supposed to. When theta is pi over 2, I've knocked it over on the ground. Right. It turns out that the force due to hydrostatic, the liquid in there exerts a force on the bottom due to hydrostatic pressure. And this force is given by rho r squared r sine theta. Actually, that's a real formula. You guys would be able to, when you do Calc 2, you'll be able to. Now, this is sort of intimidating, right? This is actually not difficult once you get past the fact that it's kind of like wooden, because there's only one variable, it's theta. It's the only thing that changes the problem. The radius of the barrel doesn't change. The density of the goop in there doesn't change. H doesn't change. None of that changes. So the variable is theta. What we want to do is we want to maximize this. And actually, this is an easier maximum problem because you don't have to figure out what the formula is, right? Really, the challenging one of the problems is draw a picture and say, oh my gosh, you got to figure out what the formula is. Here it is. What? This is an important part of the step here. What is the playground thing? We need to figure that out. We want to maximize the force on the bottom of that barrel. You know, I don't know about you, but naively, I would thought kind of first and standing vertically. That would be the forces the most on the bottom. But it's not. The tipping actually makes some of this deeper, which is harder. What are my acceptable values for theta? What's my playground? 0, right? The barrel can be standing up. That's one extreme. And what's the maximum value of theta? Well, pi over 2 will cover it, right? Because if you go to pi, you start picking it up and you're doing the same thing again, right? It's just starting the bottom of the top of the barrel. So that's going to be my playground, right? And this is kind of cool because this is a continuous function on the closed interval. So this is one of the ones where all we got to do is find critical numbers and check it, right? So let's do this. Let's take a derivative. Rho pi r squared, just a number, digging that. R root of the sine is cosine, root of cosine is minus sine. How about that? So I'm going to say this derivative. Make it later. I'm going to find one critical best. Notice that this thing is never undefined, right? I mean, it's just some number times cosine sine. So let's set this equal to 0. And if I set this equal to 0, I can cancel that out. That's not 0, right? So that's gone. So I basically get this really nifty equation, r cosine theta minus h sine theta, 0. So I get r cosine theta equals h sine theta. And let's see, r over h is 10. So there's my critical. If we take the inverse tangent of r over h, now of course r and h are both positive constants, so r over h is just some number. Put in your calculator, take the inverse tangent. That's going to give you an angle between 0 and pi over 2. Right? There it is. That's your critical. Did you work this problem? Did you have a hard time like figuring out? Because the planing is going to be the hard part in certain sense, right? I'm going to show you a couple of approaches to this. But is everybody with me? Got only one critical number. Here it is in the range, right? So let's check out what the force is. We need force when it's standing up. We need force when it's lying down. We need force at this crazy angle. By the way, I can tell you that this will give you maximum force. Look at the first derivative. Right? This, I'm going to try to plug in, but my range is from 0 pi over 2, correct? I have one critical number, whatever this is, in the middle. Everybody agree with that? I tell you, this is going to get us maximum. Because what happens, theta is stinking close to 0. This is almost 0, right? This is positive, So I'm gonna have positive. And what happens when theta is stinking close to pi over 2? Well, that's almost 0. And that's negative. Negative times positive is negative. So this should give a maximum. There's no doubt. And since that's the only one on the interval, you have to have absolute maximum. But let's see what happens when we plug in. Plugging in 0 and pi over 2 are not too difficult. When I plug in theta equals 0, and remember plugging in the function derivative. Plug in this, I get rho pi r squared h. Rho pi r squared h. When I plug in pi over 2, this bit is dead, and I get rho pi r cubed. By the way, which one of these two is too big? It's bigger. It depends. It depends on which is bigger, H or R. Right? If H and R are the same thing, this is a tie. If R is the bigger one, this is 2 R's and another R, and this is 2 R's and an H. If R is bigger, this one wins. If H is bigger, this one wins. But this one's going to be bigger. But here's the problem. For the last one, we have F of inverse tangent R of H is equal to rho pi squared over sine inverse H. H cosine. Anybody know how to compute those? Sine inverse tangent. You may have seen this, maybe. Depends on how big. You may have seen this. I don't know. I'm going to show you how to do this. Just for convenience, let's call this angle theta. This will actually be useful. Let's just call that. So let me write that down. Theta is the inverse tangent R over H. And so that means the tangent of theta is equal to R over H. Right? I'm going to use this piece of information to draw the triangle. So I right triangle, and I want my tangent of theta R over H. See my beautiful right triangle with tangent R over H? What's the missing side? Right, Pythagoras gives me this. Okay. Now let's go back and see what we want. Really, what we want is sine theta. Let's look at this here. Can you read that triangle and tell me what is sine theta? So it's R over square root R squared plus H. And the cosine of theta is H over R squared plus H. Square root, that is. Square root. So now, to do this, this is rho I R squared. R sine theta, so that's going to be R squared. Over the square root R squared plus H squared. Plus H cosine plus H squared. And And this is rho r squared, r squared plus h squared over r squared plus h squared square root. So the missing piece there, that cancels out on this side. Now let's review. What we have is we have f of 0 is equal to rho pi r squared I'm sorry. F of pi over 2 is rho pi r squared times r, writing out the r cubed dramatically. Right? And this one, f of theta, this middle, is rho pi r squared times the square root of r squared plus h squared. You see why this is the biggest now? Because this is a little bit bigger than r, and it's a little bit bigger than h too, right? Because this is only r, this is the square root of r squared, this is the square root of h squared, this is the square root of r squared plus h squared. So it's a little bit bigger. But again, before we figured it out, we kind of predicted it was going to be a maximal, right? Just thought it would be bigger. Everybody okay with that? So when you get to this, I'll give you another problem. This is kind of the brain here. How many of y'all drink like a Coke from the can? Ever done that? Everybody's done that, right? Here's a question. When are you most likely to spill your can of Coke? Right. I know the Coke can. When you start drinking your Coke, the center of mass is dead center, right there in the middle of the can. Pretty high, pretty likely not. But then you drink. Well, as you drink, what happens? Now you suck some of the liquid out after you drank it a little bit. So the center of mass goes down a little. Agree? Because it's become more bottleneck. Now, you keep drinking until your can is empty, and the center of mass is back to the original position. When it's full of liquid, it's dead center. When it's empty, it's dead center. But as you drink it, it goes down. So there has to be a point where it turns around and comes back. And that point, that minimum point, is where you're least likely to spill your Coke because your center of mass is lowest. Where does that occur? You can actually in Calc 3 or in Calc 2, you'll actually be able to figure this out. But I'll give you kind of a way in. And when you think about it, it kind of makes sense. And you can check this when you get to step in Calc 2 next time. But as you drink it, everybody agrees that the center of mass goes down, right? And what happens is drink some, it drops some, drink more, it drops more. But at some point, since the liquid is going to zero and the center of mass has to come back up, there is a point where the center of mass is right on the surface. And that's when the release line. When the center of mass is right on top of that surface of liquid, that's when it's as low as it can go. And if you think about rates of change and stuff, you can probably talk through this. We got big. So say here's something right. Forget it. Okay, what else?
Are they like water here?
Was it? I would say. You should know, you should be pretty fluid with simple things, right? If I ask you to do what's the antiderivative of x again, what's the antiderivative of sine x, or something like that, it should be the antiderivative of 1 over 1 plus x squared. Like, so know the derivative so that you put it in reverse, right? For example, derivative of the inverse sine of x is 1 over the square root of 1 minus x squared, right? So if I ask you what's the antiderivative of 1 over 1 minus x squared, you say, oh, that's the thing that's inverse sine. It's the derivative of inverse sine, it's the antiderivative.
I saw it in the textbook, it had something like a antiderivative, like a number at the top of the sign.
Well, actually, I'll go with that. We definitely got up some.
So if you see this like a window, this is down. If you worry about stuff, this is down.
Well, I mean, it's fair game, and I'm gonna put, there'll be something up there. So, are you looking at this right here? Okay, so. What do you think? Okay. So, well, this one's just power of y. So, see, like, for example, this all, if you look at 6 over 4. Say? You'll see things. Let's see. Three of those. This is the first thing we'll do. 4 out. I pull the 4 out of what's in the radical and then square root. Well, that's just, I mean, you can algebraically do that. Right, right. So let me do one more step. This is 3. And this is 3. So this is 3 inverse sine of x plus x. But almost everything that you're asking to do back there, it's just, it's either, it's this kind of manipulation. I was interested in this. Square minus. Yeah, here's one. How would you do this? Yeah. Any ideas? You're only saying you're. Because I haven't taught you anything about how to deal with antiderivative fractions unless you already know some formula. Like, for example, the derivative of the inverse tan of x is 1 squared. I haven't told you how to deal with stuff like this. So there's got to be some algorithms that don't say what does. Anybody see how my factor was top?
Square.
I think so. So you can actually factor this. Now we should.
Yes.
Mhm. And all of a sudden, this is doable. Because you can do those antiderivatives separately. You just adding, well, subtracting. What's the antiderivative?
I don't know what that is.
Right. Yeah. T squared. There you go. T to the 2 over 2. T to the next power, right? So T 3 is T to the 4 over 4. Now, what's the antiderivative of thing? So now you write your answer down and you say, oh, am I right? Check yourself, take a derivative. You get back to the previous step. Right here.
Okay.
Yeah, it's T to the 2 divided by 2. Okay. Let's go. Okay, sure. The questions I want to ask you are probably, they're not going to be computationally intensive in following sense. I'm not going to ask you, there might be some problem in your homework where it's like, okay, start from the first approximation and do 3 iterations. I'd only ask you to do one to show that you know how to use the one. I don't really care. I'm going to ask questions that test your understanding of it, right? So, for example, oh yeah. So this is like one quiz that yeah. This is very close. So suppose we have this thing here. This has a maximum at minus 1, 2. Minimum at 1 minus 2, 0, 0 is inflection point. It's got loops here at minus 3, 0. Yeah. So notice you'll know how I got the roots where across the axis. Set that in. Okay, that's good. So what happens at this? I do Newton's method, it's still getting close. The Newton's method approximation is approaching from the bottom or from below, from above. Well, if one of our approximations is right here, I call it easy line, it's gonna be there. And maybe it's right here, this easy line is. Looks like it's a little to the right. So it's above, right? Because the function actually is increasing, it's concave up here. So the tangent lines are below. So when the tangent line takes a shot at the root, it misses, right? Because of the concavity. Because the function's curling back this way and the tangent is straight. Right? How about here? Here it looks like they do communicate, right? Because right here, if my first estimate is here, my second estimate will be closer, but still to the left. And actually, if you're up here, it's a little worse. I mean, what happens here? And I apologize for the second drawing, but the fact this is a point of inflection. What again? Check frogs. Well, because no matter where you start, here, this is concave down, decreasing. So it actually shoots it here because the concavity actually changes. So it shoots to the left. Now you get over here, and now it shoots to the left because the concavity here is up. Right? So it tests that, right? Start with anything that's close to 0, like 1/10 or 100 or something like that. If it's 1/100, when you do that iteration in Newton's method, get 0, you'll actually get slightly negative. And if you start with a small, slightly negative number, it shoots actually to the other side and get you a slightly small positive. So it goes back and forth. It sort of wiggles in closer to 0. And then the important thing about that is there's a concavity change. That means we're not there yet. I mean, you don't have to worry about that. We'll get that in chapter 5. So, oh yeah. So if you've looked at my interval signs, you know, if there's numbers on it or whatever, and a lot of those intervals you're not able to get. So.
Are you gonna? How to do the
I'm gonna get to that later today. All right, that's a great question, actually. And it's dealt, yeah. We're gonna do something called integration of parts. It'll help to deal with that. Yeah, so if I ask you, so getting back to your question, if I ask you something about Newton's method, I don't expect, if I ask you some theoretical question, I don't expect full mathematical rigor. Draw me a picture, explain to me why you think, oh, this is what I think happens, and this is why I think it. I'm good. Okay, so let's I don't know. So the quiz today, we looked at x cubed minus 3x. Does everybody come with drawing it, inflection and roots and all that? Okay, so we talked about Newton's method. It says, for what positive choice of x0 does Newton's method fail? So again, I want to build this drawing a little bit. So we have f of x. All right, so now, I said, for what positive choice of x0 does Newton's method fail? Well, I wonder if anybody said one. Yeah, I should have said, in that quiz, I should have said, what positive choice other than zero is work, other than one is work. If you're over here on this side of one, the tangent line shoots you over here, you'll be closer. If you're on this side, you shoot over here. Now, the closer you are to horizontal, you can shoot far enough over here to where you get close to this way. Right? For example, this start to work this way. Right? But as you move down this way, your tangent line starts to the x-intercept starts moving down here. And that x-intercept is -1. Because at -1, the derivative is 0. So if you can find the point right here, very well, we'll call this point x0, f of x0. Start doing Newton's method. Here you go to 1, and you're done. Everybody agree with that? Because now the tangent line here is horizontal, and the formula blows up in your face. Everybody understand? So really what we're looking for is the point here. So let's say, so what is the slope of this line? There's two ways to do it. How do you figure out the slope of this? Rise and roll, right? Let's do that. This is the point, x0 cubed minus 3x0. And this is point -0. So the slope is this minus 0 over x0 plus. What's another way you slope that? All right, and what's the tool that the associated function is on the slope of tangent? Derivative. This is also should be f prime of x. see f prime of x is 3 plus 3 x 0 squared. So I get this equation here. Now just try to solve this. X 0 cubed. It's 3x 0. Multiply this here. 3x 0 cubed. 3x 0 plus 3x 0 squared. Now I get a little bit of that here. 3 and 0 is killing me. So x 0 is a root of 2x cubed, 3x squared. So that's the governing. It looks like from our picture and the way I explained that there should only be one real root to this. You all know this, if you have a cubic polynomial, like you have here, how many roots can it have? How many real roots can it have? It can have as many as 3, and it has to have at least 1. I claim this one only has 1, as I sort of suspect in my picture. So continuing on, I think, into so there's your cubic polynomial in C. It says for this function, explain why there's only one root. Well, let me just graph it. And actually, I'm not even going to use the second root because all I have to get from the graph is to demonstrate that it's got one root. And only one. So notice P of x is 2x cubed plus 3x squared minus 3. And so P prime of x is 6x squared minus 6x. 6x. That's minus 3. So I have two critical. 0 and 1. Great. So let's see what this looks like. I'm not even going to worry about it. There's too much about this. What happens when you're between 0 and 1? Something like half, positive, negative. What happens if you're beyond 1, 2, positive, positive? What happens if you're less than 1, negative, negative, negative? So F is increasing, decreasing, decreasing. So this gives me a local max. This gives me a local min. And these points are important. Have a local max of 0, negative 3. Local min at 1. Oh, boy, really help me out there. Hey, I completely freaked out here. Y'all see what they say here? We should be positive. Yes, thank you very much. Is that safety? Back very early. 0 minus 1. There we go. Better. Let's try this again. There's 6x. What happens if you're on this side of 0? plus plus. What happens if you're in use negative on that? Negative, positive. What happens if you're on this side of -1, so -10, negative? This gives local max. Local min here. This occurs at -1 blank, 0 blank. 0 minus 3. And -1 minus 2. So notice that. Here's what this function looks like. And by the way, notice that this function becomes positive after a while. But in fact, it goes to infinity as x goes to infinity. So here's what this function looks like very primitively, which is all we need for our purposes. -1 minus 2, 0 minus 3. That's a local max. So it has to be something like this. That's a local min. And then it keeps going up forever. So it can only have a plus 1 root. It's always increasing after that local min. And there you go. In fact, your root happens before you hit 1. It's actually at 1, you're already 2 away. So that's not a very good scale, but there's only 1. Yeah, that's right. I tried to figure out this. I used 2 ways to get the slope of the line that connected a point on the original cubic to the point -1, 0, which is where Newton's method failed in the next step. Okay, other questions? Yes. Number 1 on this 12. Okay, so let me give you kind of the big picture here. Cylindrical can is to be constructed containing a constant volume V greater than 0. If the finished can has radius R and height H, find the value of H over R that minimizes the surface area of the can. First draw and label a picture and describe the function of the interval, and then optimize. So I'll just go ahead and do all that once. So here you have and some radius R, H, And the volume of the can is based on the height, right? And this volume is constant. Right, because, maybe I'm like a, I don't know, dog food salesman or something. I want to have my cans of dog food, and I need them to be 16 ounces or whatever it is. But I want to figure out what's the smallest can I can put it in. Right? I want to minimize the amount of material, the surface area that I use. So what we're trying to do is we're trying to minimize surface. What is the surface area? Okay, let's get the surface area first. So there's pieces that make this up. All right, so what are the important pieces? We've got top and bottom. Right? So what's the formula that takes care of the area of the top and bottom? Right, it's two circles, right? So two. Great. What about the area that goes along the cylindrical side? No, remember that we cut this open, side, take a pair of metal shears, cut that open, put it on the table, pound it out flat, and it will look like a rectangle. Right? The rectangle that pounded it out have height h, and I guess the only thing I need to know is what's width of that. What is it? So does everybody understand what I did? Cut that can out. Right. And the height's h, right? So what's the length across? Should correspond, shouldn't it? The circumference of that circle. Right? Everybody agree? How far I can roll that out flat corresponds to the circumference of the circle. I agree. So I've got this. Now I've got a choice here. Well, so what problem do I have at this juncture? Too many variables. You got to overcome them. A choice is, and what am I going to use to get rid of one of those variables? Right, we've got this fixed volume. What would you rather do? Solve for R, put in for R, or solve for H, put in for H? I'm totally into the H thing, right? Because H just appears one place, R is more complicated. In fact, you solve for R in this, you have to do a square root. Nobody wants to do that, right? Now, if you can do it and you're feeling like really full of beans or something, you want to really practice, you can do it that way, but do other problems first. So I get H is V over pi R squared. So I've got a new and improved surface area of 2 pi R squared plus 2 pi R times this mix. So that gives me 2V R is what's done. Pi R. Everybody okay? So now what should I be thinking to do now? Yeah, let's see what the playground is. How small can R be? Well, there's kind of, so here's a couple places to catch. First of all, there's a dead giveaway. Would everybody agree I can make R pretty small? I mean, I can make some stupid looking candles strong, right? Can I make R zero? No, I can't. Problem here, and actually that comes from the problem here. Remember, my volume is supposed to be, I'm supposed to hold 16 ounces of my dog food, right? If and B is, it says it's bigger than zero. If R is zero, there's no way I'm fitting anything in. So now this time, of course, it's R is zero. Now, how big? By this constraint here, it doesn't appear that there's anything, right? I could make R 17 miles and it's super, super short. I'm not gonna be able to market that, but I can do it. Well, these are one of those noxious ones, because what's noxious about this is once I find the critical number, I can verify what I'm getting. Oh, what are we trying to do here? Minimize. You always want to make sure that what you've got is a minimum if that's what you're looking for a nice. Because you don't want to make, you're supposed to be making the smallest key, you want to accidentally tell the factory to make the biggest key. Right? So let's take a derivative of this. Got everything set up. See, 4 pi r minus 2b. And that's the derivative. Now, obviously, there's a place where r is a problem, and that's r equals 0. Lucky for us, that's not our range, so we don't worry about that. So all we got to do, find critical numbers, set the sequence. And if I do that, 4 pi r is equal to 2b squared. It's something like r cubed is equal to 2b over 4 pi. So that's b over 2. So I get one critical number and only one critical. Root of whatever my volume is. Now, let's analyze this real quick. My range is from 0 to infinity and beyond. Don't let it bother you. But you don't have any numbers for this. Fine. Look at the derivative. There's only one critical number, so this can only change sign at once. Do I agree with that? It's either all positives, all negatives, or it changes sign. What happens when this thing is stinking near 0? R is very, very tiny, 1 over a billion. That's almost 0. And that is huge negative. Agree? What happens is R just goes off toward infinity? Big, 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 big. Maybe R is zillions and zillions. That's huge. And that's going to 0. So it's positive. So my function decreases and then increases. So this is a local min, and it's an absolute min on the minimal 0. Because think about what's happening. You start somewhere and you go down. Once you hit the down, you go up forever. All right. So that has to be an absolute min. I believe the final question was find the ratio of H to R. Is that right? And actually, I think this is going to make sense. Notice at the critical number. Well. There, as far as that. Notice H is B on pi r squared. Because of this. Divide both sides by r. Right. So there, put r and pi. Notice at the critical, r cubed is b over 2pi. So I can replace that on b over 2pi. So h over r is b over pi is b over 2pi. And there is a great installation. So in other words, if you have one all pins of this volume, if you want to make the surface area as small as possible, the ratio of height to the radius is exactly 2, which means the diameter and the height. That's why you don't see it very well. I mean, pins on it. In the purpose. Yeah. Other questions? How do y'all feel about the optimization? Feel like we get good set up?
Like it depends. Probably for this one, if I remember the date, the surface area and the volume, I could get to set up. I could at least one person.
Yeah, so you should probably practice figuring out what this kind of formulas are, but I don't want to leave you high and dry. Moving forward, right? I mean, when things involve like circles and cylinders and stuff like that, it'll probably help you in 1080. You know, I don't want y'all to get wiped out with like shooting back. So if you need something, let me know. Yeah, so you can always get information from me. It's just whether it's free or whether it charges points. Okay, other questions?